Hi everyone, Mr. Companion here. We're looking at lab number 6 today, so let's jump straight in. So this is the Finding Epicenters lab. Earthquakes are vibrations caused by large releases of energy. The energy released radiates from the point of the origin, the focus. The term epicenter is used to describe the location on the Earth's surface directly above the focus. Earthquakes generate several types of energy waves that radiate in all directions that can be recorded onto seismograms. Two of these waves are used to locate epicenters. Here we have a P wave and here we have an S wave. P wave is our primary wave. It comes first, it comes fastest. S wave is our secondary wave, also known as a shear wave. This is the more damaging wave. This is the one that causes the damage to the buildings. P waves, primary waves, vibrate back and forth because they travel faster and arrive at the seismograph station first. S waves, they go perpendicular, side to side, they move slower, but they do more damage. P waves and S waves start out together from the epicenter. For an earthquake, for a nearby earthquake, the P and the S waves arrive with little separation. So the closer these are together, the closer that the earthquake is going to be to that seismic station, the station that recorded it. You can see here between the P and the S, there's quite a bit of space between the two. It happened over the course of several minutes. So we know that these two, since they're far apart, means that station A was rather far away from the actual epicenter. Okay, so I'm going to let you read through this. Just one big important thing that we want to pull away is right here. We always have to do it in the hour, minute, second format. Step 1, the following 4 seismograms are from the same earthquake detected at 4 different seismic stations. Use these seismograms to calculate the time difference between the P and the S wave arrival times. Record all arrival times to the nearest 10 seconds. So here are our 4 that we have on here. Let's zoom in a bit. We've got Oklahoma City, Denver, Tampa, and Chicago. Now, if you look at Oklahoma City, the time that the P wave was first felt was some point after 36. Now we see the hours of 2 hours, 30-something minutes, 31, 32, 33, 34, 35, 36. Now, since we can tell that the numbers are increasing as we move to the right, you can determine that, well, we know it's going to be 2 hours, 36 minutes, and a certain number of seconds. So over here for our P wave, we come down here, for Oklahoma, we would probably write down, let's zoom out a bit, we would probably write down 02 for the hours, 36 for the minutes, and I wouldn't say that that's dead in the middle, right? Right exactly in the middle might be 30 seconds. I'll say that it's 25. We'll do the same thing for the S wave. 2 hours, 02. For the minutes, 39. And for the seconds, well, now we're on the other side of that 30-second part in the middle. Remember, each minute is composed up of 60 seconds. So if I know that's a total of 60, and I know that's 39 and 0 seconds, and I know that 40 is 39 and 60 seconds, right in the middle would be 30. You can call that 35, you can call it 40. I'm going to go with 40 for this one. All right, and then that leaves us with a little math to do. So now we have to find the lag time, and that's what the S wave minus P wave time is. We call that lag time. So the format is, it's always going to be S take away P, S wave minus P wave. Our S wave here is 02, 39, 40 minus 02, 36, 25. Now, you always do it in chunks of 2. So in this case, it would be 40 minus 25. Well, yes, you can do that, and that would give us 15 seconds. 39 minus 36 would give us a difference of 0.3 minutes. And for the hours, we've got 0.2 minus 0.2. That would give us 0.0 hours. So our lag time, that's supposed to be a G, lag time would be 0.00315. Now, you'll do the same thing for Denver, Tampa, Chicago. Pretty straightforward, right? So like for Denver, for example, this one's pretty much exactly on the 38. I would say 0.23800. Now, to calculate the distance to the epicenter, again, pretty straightforward. We're now going to take a look at Earth Science Reference Table, page 11. All right, so there we go. And we want to do it for 3 minutes and 15 seconds. Now, the procedure here is to get a scrap piece of paper, line it up along the y-axis, try to keep it straight, mark the 0, label it, and the time was 3 minutes and 15 seconds. We're going to be at 3:15. Now, one thing you want to keep in mind is that each one of these is a minute, but each little guy in between is a 20-second interval. So, for example, if we really zoom in here, let's try this, we really get close, you could see that that would be 0 and 0 seconds. This would be 0 minutes and 20 seconds. And that would be 0 minutes and 40 seconds. 0 minutes and 60 seconds is the same as 1 minute. All right, so that's where you get that. So let's try and line these up. Once again, you're going to mark off your 0, and we're looking for 3:15. Well, if that guy right there, the one right above the 3, is 3:20, I know 3:15 is just going to be shy of that, and I would mark it right there. So I've got my first one marked for the 0, my 3:15, we're marking right here. It's 3 minutes, 15 seconds. Now, you're going to slowly drag to the right. Now, as you drag the scrap piece of paper to the right, you want to try and keep the bottom one on the P. And as we go up, you'll find that just about right here, maybe? Yeah, that looks pretty good. It looks like we have the 0 mark touching the P line and the 3:15 touching the S line. And if we follow it straight down, that brings us to this spot. Now, it says here epicenter distance times 10 to the third. 10 to the third, which would be 1.0 times 10 to the third, meaning 1, 2, 3 decimal points over, that would mean 1,000. So that's exactly what that guy is. So that's our 1,000 mark. That right there is our 2,000 mark. That's our 3,000 mark, etc. Now, if that's 1,000 and that's 2,000, well, that means that this spot right here would be 200. So each intermediate mark on the bottom is going to be 200 kilometers for each small line. And on this side, it is 20 seconds for each small line. Okay, great. So in this case, if that is 2,000 and that's where we ended up, we would be at 2,200. So let's go back to our lab paper. And for Oklahoma, we're looking at 2,200. Once again, do the same for Denver, Tampa, and Chicago. Now, step 2 here explains how to use your drawing compass. Now we have our safety compasses, which look a little bit like this. I don't know which way I'm pointing. Those are safety compasses. I'll insert a video showing how to use those just because I don't have one with me right now. And that's what you would use to draw around your first point. So your first point would be Oklahoma City. So what you'll do is you'll draw, starting at your 0, down here on the scale, out to 2,200. Now, funny thing about this scale is that each one of these little intermediates go by 100. That's not typically normal, but just make sure you're paying attention when you do these things. So that's our 2,200 kilometers. This right here is 0 kilometers. So what you'll be doing is creating a circle with a radius of. All right, so I used a traditional compass to draw this one. What I like to do is I label the spot that I did. So this was Oklahoma City. And I like to label the distance that I did. So in this case, it was 2,200 kilometers. All right. Now you'll do that again, obviously, with Denver, Tampa, and Chicago, and there'll be one spot where all 4 of those circles should meet. And where they all meet, you're going to put an X. Now, step 4 is origin time. Now, in order to calculate origin time, it's pretty simple. The formula is just P wave arrival time minus the P wave travel time, giving you the origin. Now, using your travel time graph, how long does it take a P wave to travel 4,000 kilometers? Let's find our P wave. That's this one. And let's find 4,000 kilometers. So there's the 4. We're going to go up, bump the line, come across, and it looks like it's about 7 minutes. So in this case, 0, 0, 0, 7, 0, 0. Now, if the P wave from an earthquake, 4,000 kilometers away arrives at our station at exactly 12 o'clock, when did it start its journey? Well, think about that for a moment. If we felt it at 12 o'clock, and I know for a fact it took 7 minutes to get here, all you got to do is a little bit of subtraction. So here you're going to take away 7 minutes from that 12 o'clock. So just in the margin here, I'm going to do the math. 12 hours, 0 minutes, 0 seconds, minus 0, 0 hours, 0, 7 minutes, 0, 0 seconds. 0, 0 minus 0, 0 equals 0, 0. 0, 0 minus 7 can't do, so you got to borrow. 12 becomes an 11, and we're going to bring over 60 seconds. 60 seconds plus the existing 60 seconds is still 60. 60 minus 7 is going to be 53. And 11 minus 0 is 11. So the origin time, the time that the earthquake actually occurred, was 11:53:00. Okay, and this brings us to our final part of this earthquake. It says here, use this technique to determine the origin time of the earthquake recorded in your data table. You could check yourself by doing the calculations on at least 3 of your stations. So the first one I'm going to do for you is Oklahoma City. You're going to do Denver, Tampa, and Chicago. So for Oklahoma City, all we got to do is come back to our data table here, and we can see that it says 236.25 for the P wave arrival. You're just going to copy that back down. 236.25. For the distance to the epicenter, once again, you're just copying it straight off the previous sheet. 2,200 kilometers. And then the P wave travel time, you're going to calculate by using your reference table. Once again, reference table page 11. And you're going to calculate the P wave travel time for an earthquake that was 2,200 kilometers away. So 2,200, which is right here. We're going to work our way up, bump the line, come across. It looks like it's 4 minutes and 20 seconds. So the P wave travel time is 00, 04, 20. The P wave arrival minus the P wave travel is going to give you your origin time. So in this case, it would be, and again, I'm going to do the math in the margin here, 02, 36, 25. Take away 0, 0, 0, 4, 20. 25 take away 20 is going to give us 05. 36 minus 04 is going to give us 32. And 2 minus 0 is going to give us 02. Our origin time of this earthquake looks to be around 2:32:05. Now, if you think about it, the one for Denver, Tampa, and Chicago, they should all come pretty close to what that was. And that's what I'm going to be looking for in grading. Down here, you have a totally separate earthquake, and you just have to make your own conclusions from that. And that finishes this lab. So, all in all, a little bit of a time-consuming lab. I gave you the first one, Oklahoma City, all the way through, so there's really no excuses. The only thing that you're going to have an issue with is if you don't have a compass at home. I have these safety compasses, and you're more than welcome to use mine. I recorded this for the 2023 school year, so if you are currently watching this, and I currently have you as a teacher, and we just finished this, tutoring is on Tuesdays. Tutoring is on Wednesdays from 2:30 till 3:30. But that is it. All right. Lab number 7 is going to be more of the same. And if you have trouble, take a look at the video I recorded for that one. I hope this was helpful. Bye-bye.